Hi, everyone. Welcome to Always Coding, our weekly Hacky Hour. And good afternoon to you too, Alex. He just wrote a note. My name is Komal Devjani. I'm a developer advocate with Always AI, and I'm joined today by Eric Van Bueller. He is a senior principal architect at Always AI. So thanks for joining us again, Eric.
Glad to be back. It's been a little while.
Yes, I think everyone's super happy to have you back. So I see a lot of familiar names on our list of participants. So if you've joined us in the past, welcome back. But if you are new, Hacky Hour is your opportunity to ask us questions, anything relating to computer vision or Always AI. We're here to help. So today, Eric is here to help us make sense of the RealSense. And before we get into that, I want to share a couple of announcements and then just show you how to get started with the human pose estimator. I believe that is going to be the focus of today's application. And then we'll hand it over to Eric to demo the application that he's built. So let's get going. I'm going to share my screen. And the first thing I want to announce is we are still reviewing applications for Always AI's Model Training Challenge. So this is pretty casual, and we're going to be accepting applications on a rolling basis through December. And the goal of this challenge is we want to see you train your own computer vision model using either our gesture recognition dataset, and that dataset's available on this link as well. So I'll share this out. Or you can use your own dataset, a publicly available dataset. And we want to see you build an application with your newly trained computer vision model using Always AI's model training toolkit and our Edge IQ services. And once you've done that, you can tag us at Always AI. We are on Facebook, LinkedIn, or Twitter. And you want to just share your GitHub URL so we can review it and check it out. And use the hashtag Always Training. And select users will be invited to come speak at our Hacky Hour and be featured on the Always AI blog. So good opportunity to get some clout if you're interested in that. And if you just scroll down, you'll see all the setup documents relating to our model training services and our setup documents, as well as the gesture data set. So take a look here, and I'm going to post this link. It's just learn.alwaysai.co/model training challenge. So with that out of the way, what I want to do is just show you how to get started with Always AI. The first thing you want to do is go to alwaysai.co and sign up for an account if you haven't done so already. And once you do that, let's navigate to our dashboard. And here you can see, you can learn more about training models. So just go directly here if you're interested in that. And we have a sample project. It's the Hello World face detector. But most importantly, on the dashboard, you want to install your CLI. So you can install the CLI by clicking here, or another way is let's create a new project, and I'm going to show you what that's about. So we want to create a human pose estimation project. We'll just call it HPE and create project. Once you view your project, you'll see that there's instructions to download the CLI for your specific operating system. So just go ahead and click that. And pretty soon you're not going to see this unidentified developer warning, but if you are doing it for the first time right now, you will see that prompt. Just bypass that and you should be fine. So as you can see on here, I already have the human pose estimator added, estimation app added. So what I want to do, model rather, not the app. Let's go into my terminal, and I want to go into the directory for my demos. Okay, and then from here, I just want to copy this command, the app configure, and hit enter. Oh, I think something's up with this.
I had that happen earlier too. I think if you just delete the project.json in there and then run the configure command again, should, well, I guess you had the project ID. Yeah, just try removing that and see if it works then.
Yeah, do you think I should delete the app as well?
No, just now just try the configure command.
Live debugging, everyone.
Yeah.
All right.
There's no reason you shouldn't be allowed to use the project from your own dashboard.
Right. All right. So that's a tip for you. If you're running into that issue, just delete the project.json file. So I want to save this to my local computer, and then from here, let's just make sure I have added human pose as the model, and I have in my app.py file. So let's just hit save here. And from here, what I want to do is just AI app install, and then AI app start. So this streamer pops up, and I want to just copy it and paste it on a new browser. And as you can see, this can detect all these key points on my human body, right? Like, so this is the human pose, so you can identify shoulders, elbows, wrists, I think. So yeah, that's the human pose demo. And from here, I'm going to hand it over to Eric to kind of walk us through some details about how you can use human pose with the RealSense camera. So Eric.
Thanks, Komal. And yeah, I'm glad that you could give everyone a visual of the Human Pose app, because the app that I'll be showing in a little bit uses the Human Pose model under the hood, but it's not actually going to show the key points and stuff on the screen. So for those that haven't seen it before, it's a good visual as to what that model is actually detecting. And so what I'm going to go through is how to use the Human Pose model along with the RealSense camera to track like limb motion in 3D space. And I made kind of a fun little app where it's a dart throwing app. So it's up on GitHub. You can try it out. And I have a short little presentation to kind of start with some of the high level concepts of the app. So I'm going to share my screen if I can figure out how to do that. And yeah, feel free to jump in with any questions or anything while we're going. And
Hi now, Eric.
Sorry?
I said you should try. You should be able to share now.
Okay, cool. Got it. So let me just make this bigger. So there we go. So motion tracking with the Intel RealSense camera. And oh, I think you can still see my camera feed up there in the corner. So if you haven't seen the RealSense camera, it looks like this. And right now I've got it hooked up to an Xavier NX, which can get really good inference time on the human pose model. So I think it's like 30 milliseconds or something like that. So we're going to put those two things together to get high performance like 3D data for my dart throwing motion. So yeah, so a couple of things that I wanted to go over. Just talk a bit about the rapid prototyping I did for this, and then a little bit about the RealSense API, talk about some inline and batch processing concepts that I used in the app, and then a little bit about finite state machines, architecture, and then we'll give the demo a try and see how it works. And so if some of this is, you know some of this already, just bear with me because I think the demo is pretty cool. But these first couple bullet points, I don't even have slides for. I just wanted to preface with that I started building this app on Tuesday in between other stuff. So it was really rapid process of kind of getting it up and running. And it's not fully complete yet. I think it's about 80% done. I left the scoring for a future task. So right now it always gives you 10 points no matter what you do, even if you miss the board. But the bulk of it is done and working. And so just kind of wanted to preface it with that. I think we talk a lot about how quickly you can build stuff with Always AI, and I always like to reprove it to myself that you can actually build something cool really quickly. And like I said, I started this on Tuesday afternoon, and if you look at the Git repo, I pushed a commit, I think, about a minute before this Hacky Hour started. So that's where we're at with it.
That is true. Then, I was like, where is the GitHub repo?
Yeah.
I'm still working.
So a note about the RealSense API. So we've had the RealSense API in EdgeIQ for a while now. And one thing that was missing was support for human pose. So this app is actually using an experimental and unreleased implementation of the RealSense API in EdgeIQ that can do human pose and a few other things. And so it's set up so that if you run this app, it will work and you can get access to that dev EdgeIQ image. but you're not going to find this redone API in the API docs or anything yet. It'll be coming up in a future release. So keep your eyes open for those release notes to come out. And until then, just be cautious of implementing this API into your own app, because it might change as it comes out. But if you want to give that a try, you're welcome to. And yeah, so that's what I wanted to say about that. And one interesting thing actually about the depth piece that I wanted to mention, one thing that I kind of ran into is that in this case, I'm tracking a point on my wrist. And what I've found is that if that point's a little bit off, I instead get the depths of the back of the room. So it's, in cases like this, you kind of have to look at the data and figure out, how can I correct for these errors and stuff like that. We didn't see that as much in object detection because usually you're detecting like a whole person or something. The point's going to be right in the middle of the person. In the case of detecting a smaller object, there's a higher likelihood that you might just miss it and get 5 meters instead of 1 meter for the depth. So just keep your eye open for that if you're trying this out yourself. So I wanted to talk a little bit about inline and batch processing. This is something that comes, like a lot of our starter apps, if you've used them, they use this. I wanted to label this. This is the inline one, and these two are different methods of batch processing. But so if you consider these as the frames coming in, if you've used our starter apps, you know that based on your inference time, it kind of slows down the overall frame rate that you see output on the streamer. So in this case, we're getting the output of frame 1 here just after frame 5, and then we grab the next frame and process it, and then we have frame 6 done all the way here at the end. And that puts certain limitations on what, like the timing, how quickly you can react to events, but also it means you don't get bogged down in trying to process and catch up with frames, because in these cases, if frames keep coming in at a consistent rate, 30 FPS, for example, if you try and process every frame, you're going to be in a catch-up race forever if your inference time is longer than the interframe time. So that's where batch processing comes in. And the idea is that instead of trying to do this over a long period of time, if you know, for example, you want to understand what happens in a 1 second period of time, you can capture those 30 frames and start processing them in the background sequentially, but you know that your full time is still bounded by the 30 frames multiplied by your inference time. And so that's kind of this case right here. And we actually use that in this app because I wanted to get a finer resolution of data for the actual throwing motion. And so I collected every frame over, I think, a half-second period of time, and then measured changes in velocity and stuff over that, as opposed to just capturing one out of every, I think we were getting like 8 FPS when I was just letting it run in the inline mode. And so, yeah, so 30 frames in 1 second is going to give you much finer grained data than 8 frames in 1 second. And additionally, if you have a machine with a bunch of cores, or even in threading cases that aren't in Python, where you can actually run threads concurrently and stuff like that, you could do a batch processing like this third example, where you actually start processing each frame when it's received, but you can overlap these in different cores or threads or whatever. And you might actually be able to keep up, depending on how many cores you have, with the frame rate. And so by the time you get to frame 5 and you finish it, your first thread or core is back open for frame 6, and you're actually keeping up with the frames as they come in. You can actually do that, maintain that over, continuously. You don't have to do it in short batches like I've done in this example. But these devices don't have the capability to keep up with that in general. And one thing to note about the RealSense too is that you can actually get much higher frame rates for this. You could go 90 FPS if you wanted to. I don't remember all the profiles at this time, but I know 90 FPS is an option. And so if you were doing something like a pitcher's throwing motion, a golfer's golf swing or something, where you wanted the full frame rate of 90 FPS to catch the really fine-grained data, you could do that in the batch processing mode and still capture those frames, do the processing in the background, and still get a result in a fairly short amount of time, depending on the device you're using. So that's pretty cool method to use for these more advanced use cases. So another thing is another design concept I used is a finite state machine in this app, and I did that to kind of maintain the state of the dart throwing motion, and it makes it a lot easier to kind of isolate the different operations that you have to do in the code. And so sometimes finite state machines are very useful. Sometimes they're the opposite of that, and they make things a lot harder to understand. So you do have to be kind of careful where you use them. But this ended up being a super simple like circle one, which I haven't done too many times, but it was really nice because yeah, it's very simple. It's basically just shifting through these states. So in the waiting state, that's when it's kind of waiting for you to get in a position to throw. And it has a few things to check to determine if you're in a throwing position, and that moves to the ready state. And in the ready state, it waits for you to begin the throwing motion. And so what I did was I was measuring, at this time, I'm still doing the inline processing, so I'm getting 8 FPS, but I'm measuring if there's a sudden increase in velocity. And so if we get that sudden increase in velocity, we go into the throwing state. And in that state, we're collecting a batch of frames. I think it was a half second. I think I collected 15 frames. And then once that's done, there's this convenient state of the dart is flying. And that's when I'm processing the data, because the batch processing takes a little bit longer than it would if you were just computing it, if you were able to compute them as the frames came in, right? Kind of just what I explained. So there's a little delay, but conveniently, that's when the dart's flying through the air. And then once those frames are processed, hits the dartboard and you get your score. And I just have it wait for 3 seconds and then go back to the waiting state. So it kind of just keeps looping through this. And there's a little bit more to it, but this is really the main concepts of it and the transitions. So let's see. So, and I wanted to break out kind of the classes I made at a high level too, before I jump into the code. So the main class that's kind of controlling the state machine is the darts class. And it has these 3 other classes within it, and also some attributes. It maintains your remaining attempts and also your score. And so you can change it so that you have a limited number of attempts, and then every time you run out, it resets your score and starts you over with the max number of attempts again. So this class is just handling the state machine in the transitions. So this I made a class pose handler, and the purpose of this is to provide robust pose information based on the input RGB and depth frames, and it handles both the inline processing and the batch modes. And the reason that I kind of separated this out is because I couldn't, in like the starter app, we just kind of, write the data points out there. If we don't have them, there's just no data point there. We can't be that like loose with the data in this case. It needs to be robust. And so we need to have some notion of past values and also what we expect the values to be. In the case of like, if you're in a throwing motion and your hand's kind of up here, the depth of your wrist shouldn't be behind your body, right? Things like that. So this class kind of takes information from a bunch of different aspects of the pose and determines if it makes sense. And if it does, then it submits it as a valid like pose result that can be used elsewhere in the app. And so, yeah, yeah, so it kind of interacts with the history tracker. Now, there's probably a tighter integration that could be done, but this was rapidly prototyped, so I separated this logic out. And the history tracker is responsible for maintaining a history of the throwing motion and also all the data points in between. And so what that's doing is it's consuming the pose information and putting it in a format. I use pandas in this case to kind of put it in a table so that I could analyze the motion and velocity over time. And so I'll show that in a minute. And then finally, I have a kind of a screen handler class whose responsibility is to just draw the dartboard and draw the darts on there. So I just wanted to separate that out so it didn't get mixed up into everything else, because it's pretty simple, but it's kind of, you know, drawing circles and stuff like that. It was nice just to kind of separate it out into its own class. So I think that is everything that I have for the slides. Any questions yet? Or I'll jump into the code if there's a...
We have a couple of questions, Eric.
Okay, yeah, let's take a couple of questions.
So these are specific to the RealSense. The first one is, have you tested the RealSense in outdoor conditions with full sun, high sun, radiation over the objects in the image? And he mentioned that I have some issues with the IR projector in those conditions. So what is the proper configuration of a RealSense camera to get decent raw data?
That's a great question. The extent of my test of the RealSense camera have kind of been in my office here, and then in our office in Solana Beach, where the lighting conditions are usually fairly good. It gets kind of dark in here, but it's never sunlight shining in or anything like that. So I actually haven't you know, kind of pushed it to the limit in terms of like lighting conditions and stuff like that. I've really kept it in kind of simple conditions. So I don't know if I have an answer for that. And I don't know if Steve's on, maybe he's tried some different stuff out, but yeah, I don't know if I can really speak too much on that. Sorry.
Yeah, Steve's not on, fortunately.
Okay. I know, so we're working with some customers who are definitely going to face this. They're trying to get the RealSense camera working on a boat. So these sorts of things like reflections on the water and stuff like that, I imagine are going to be, are going to impact its performance and stuff for sure. So definitely something that we're going to be digging into and figuring out in the near term.
Yeah, and unfortunately, the question was asked by an anonymous attendee, but if you want to reach out, and I can also, like, once we have more information on that, I can let you know, like, on how to control those conditions or control for those conditions. But okay, so the next question is, why were you only able to get 8 FPS with a Xavier? What was the bottleneck?
So that's a great question, and actually, it's something that I'm actively digging into. So with the 30 milliseconds, I think we should be able to get like 10, 15 FPS. But the problem in human pose is a little bit unique in this case compared to object detection and like classification, for example, because with human pose, the inferencing is only a small part of it. Actually, you get these like partial affinity fields back and stuff, and you have to do a good chunk of post-processing to even get those key points afterward. So that's one piece, and that depends a lot on, I think, the CPU side. So I'm on an Xavier on X. The inference is happening on the CUDA cores, but then this post-processing is coming back onto the CPU. So that's one slowdown. I'm not sure. So it'll be even worse if you try and draw the pose information. That's also a very expensive operation, so something to keep in mind. I didn't remember what the FPS of Komal's app was when she ran it, but you'll see that if you take away the drawing the pose piece, it might even be twice as fast. I've already taken it away, so I've already lost that limit, but the post-processing is really the big piece here. And so one thing that we're looking into is other human pose models. I know that there's one from the Jetson team has used to get like very fast inference times and stuff like that. And so that's on my list to check out and see how integrating that works on our system. I would love to get even faster human pose operation, but yeah.
I think that's all for questions right now.
Okay, cool. So I have this Darts app pulled down, and one thing you might notice is every time you run
sorry,
it.
Eric.
Yeah.
I think actually, never mind. I thought Marty wanted to say something, but.
Oh, okay. Well, if he wants to jump in, just let me know. So I'm also, so one thing that may be useful to you if you want to give this a try is that every time it runs, it dumps a CSV file of all the output data. So maybe after I do a run, I'll show that real quick. And that's really helpful for kind of understanding why it made the decisions that it made. But besides that, the main piece here is the app.py. Oops. So first, so
Hey,
actually I'll start kind of, oh, okay,
sorry,
Marty.
I think he's here.
Okay, cool.
It's actually good.
It's actually Steve.
And Marty.
I'm with Marty sitting in his office. We were on the YouTube channel. So my experience on outside is the RealSense camera performs better indoors than it does outdoors on it. You also really have an effective thing unless you have the new 455 in the platform of 10 meters. So you have an effective rate of 10 meters away on any object and things like that, remembering. And so then when you start to take it outside, it just was indicated on the infrared side and things like that. You may even see that it probably gets down to about 6 meters and so forth. And I've seen conditions where at sunset it wasn't great and things like that too. And I've had issues with being outside in the sun with the system. So I don't know what else to say other than that. So yeah, results are much better when you're indoors.
Okay.
Okay, cool. Thanks, Steve.
Yeah, thanks, Steve.
And then I'll let you answer why you can't get above 8 frames per second. So I have no idea on your application on that.
Yeah, there's a comment on here that says one way to improve the FPS with an estimator like this is to use some visual processing unit like an Intel neural compute stick. You can offload.
But the Xavier's got the GPU on it. I don't buy it. Yeah. Did you use a Tensor RT model?
Yeah, I'm using the Tensor RT model. I mean, this is the same experience I had with the Jumping Jacks app. I think it's a limitation of this model itself, right?
Yeah.
It's converted to Tensor RT, and so this is pretty much the inference time only tells part of the story. I think that's the thing. Like if you look at that 30 millisecond inference time, you expect it to be much faster overall.
And again, when we ran object detection under Tensor RT, effectively you get up to 7 milliseconds response time on the Xavier XM. And you're used to expecting that on a MobileNet SSD. It'll actually even slow down when you go to a YOLO and more types of processing. But yeah, you'll see that, and it'll change, as you say, different model configurations and architectures. So anyway, that's it. I'll go back on mute and let other people come back in, but I'm here now. I was over on YouTube, guys. Sorry.
Cool.
Thanks, Steve.
All right, so just briefly, just wanted to show. So if you've seen our starter apps, that you usually have this main function with the setting up of the camera and the streamer, and then the loop. And in this case, it's been really simplified because what we're doing is we're creating that darts class and then just sending the RealSense frame into the darts class. And then from the darts, or the darts object at this point, from the darts object, we're grabbing image and text to send to the streamer. So there's really not much to see in this loop. It's really simple. If we get to the darts class, there's a bunch of initialization. But this update function is the most interesting, and this is where the state machine is. So basically, we go through the states of waiting, ready, throwing, flying, and then finally complete. And at the end of each of those, there's the transition checks. And so in this info is setting up the text to be displayed out here in the streamer. And yeah, and it's designed in such a way that I tried to make it kind of non-blocking so that it would loop through every time there's a frame and not get stuck on, processing something or doing a sleep here or there. So I used kind of wait counters for states that I wanted to last for a period of time. One thing that I ran into is that apparently you can't, so I was doing inline processing on the main thread, and then I'd created a background thread to do the batch processing. And apparently you can't do that on CUDA, or at least the way I was doing it was wrong. So I rapidly worked around that and made even the batch processing kind of happen after the frames are collected. So that was kind of a bummer, but that's one thing to note. So I'll just step through this real quick. So in this waiting state, the thing that I decided to check for to get into throwing position was that your right wrist is, and it's going to look like it's backwards, but if you remember Steve's Hacky Hour a while ago about how the X and Y coordinates in OpenCV work, the 0, 0 point is up here. So Y being increased brings you down. So here I'm checking if the Y value of the right wrist is below the right eye and above the neck. So I found that I usually like held my fake dart up kind of by my face. So that tended to work pretty well. And then I tried to also determine if your hand was fairly still. So I'm checking if instantaneous velocity is less than 0.01 meters per second. And one thing to note too is that this velocity I'm measuring is purely in the depth space. It's not taking X and Y into account. And so one thing I did in this state machine is kind of because we're working with, a few frames, we have these, we have this limitation of how fast we can process the frames. So instead of wait for a new frame to come in to move to a new state, I allowed it to jump directly to a new state. So you'll notice these are ifs and not elifs. That was by design. So if we're ready to go to the ready state, we can fall straight down into the ready state. And here we're waiting for the throwing motion to start. So I just kind of arbitrarily picked an instantaneous velocity that was a little bit large enough that you wouldn't, accidentally hit it if you were just moving your arm a little bit around. It seemed to work pretty well. And so from there, we go to the throwing state. We can fall straight in. And here, one thing I didn't mention is we were directly getting the pose data and putting it into history in these first two states. And so we're tracking that pose data inline and getting the history. So it is blocked a little bit on processing that one frame. Once we get into the throwing state, we submit the frame for batch processing and we just increment a throwing counter. And so once we get to the throwing counter max, which I set to 15, then we bump over to flying state. And the flying state is where we're actually doing the processing, the post processing and getting the pose information from those. And so you'll see that we're getting the batch results. I'll show that function in a second. And then we're processing those results. And that is determining the dart position, getting the score, and then adding that dart to the screen. And finally going to this complete state, it basically just waits for, I think, 3 seconds or something. So you can see where your dart is before you have to get ready to throw again. And it also does some checks on the remaining attempts, like it resets your score if your remaining attempts is down to 0. And these are all configurable things you can change. So I think the next interesting one to look at is the pose handler. So here is where you would usually see this in the starter app, just right near the top. We're creating the pose estimator by loading the model and the engine. And in this case, I wanted to make it so I could go back and forth between my laptop and the Xavier NX. So if we're on an Xavier NX, it loads this model, the TensorRT specifically for Xavier NX, and uses TensorRT engine. Otherwise, it just uses the human pose Onyx model on the DNN engine. And I was seeing about 300 milliseconds for that. So it was good enough to prototype with, but it definitely had a lag in detecting the throw. Basically, one of the problems I ran into there is that by the time it detected I was throwing, I would have already missed too much of the throwing motion just because that 300 milliseconds is a good chunk of time to lose just to see if you've actually started that throwing motion. So good enough to prototype with and iterate on, but not good enough to really tell if it was working. And so let's see what's going on here. So one thing, let's jump to the get pose data. So this is the basic function that's going to do some quick processing on the pose result and decide if it's valid or not and dump it into this, dictionary that it returns. So we're getting the pose results. And first we need to make sure that we even got any poses. And I've been standing in front of the camera the whole time. So it's always going to see some part of me probably. And then I'm grabbing the key points from that. And so the key points are, I think I have the API open. Let me see. Yeah. So these are all the key points. These are all the different parts that you can track. And so just head to the docs if you want to dig more into that. So like I mentioned earlier, I'm tracking the right eye, the neck, and the right wrist. And you could make this adaptable for left-handed people. I was just working fast and I'm right-handed. So yeah, feel free to tweak this if you're a left-hander. So what I'm doing is getting the data point, getting the point data from the right eye, the neck, and the right wrist. And that's this function up here. And what it's doing is it's checking to see if we found that point. And what happens is if human pose doesn't detect a key point, like it can't, like my wrist is below my desk, it can't see it. It's going to come back with -1, -1, which you need to have a specific check for, because if you just expect that those are valid coordinates, you're going to get some really weird outcomes with negative numbers and stuff, which, you know, I've run into before by not checking that. And then from there, we can directly compute the distance from the RealSense frame. So let's see. And then if we don't have that data point, what I'm doing is just at this time returning what was previously seen. And so that's initialized to all zeros. But as we go along, we save the last data, we overwrite it with the new one that's detected. And so we don't get kind of bogus points in there. Let's see what else here. So another thing that I mentioned this earlier, but one issue I ran into was with the depth kind of missing the wrist and hitting the back of my office instead. And so one check that I added was to see if the right wrist depth was greater than the neck, because I never expected that to be the case. And if that's the case, then I slam it with all zeros, which tells me later that I should ignore this data point. I have some checks later that look for zeros for the depth and stuff like that. Now, there's probably a lot more sophistication you can do with this check, and more that I wanted to do, but just didn't have the time to do. But this is kind of the quick and dirty way to get it up and running and working well enough. So on the other hand, for the batch results, this code is a little bit not as clean as I would like, because it was originally sending stuff to a thread, which was working great on my laptop. But then I quickly changed it to just dump everything into a list. This batch frames is just initialized to an empty list. So when we submit for batch processing, we're just dumping it into that list. And then when we get the batch results, we're actually iterating that list and getting the pose data for each one. So it's not the true batch processing that I wanted to build into the app that I talked about in the presentation, but it works because the Xavier is fast enough to handle this. So you'll see that it still works pretty well. And there's definitely improvements we can make here. Okay, so look at the history tracker next. So like I mentioned, this one is keeping a history of the wrist, eye, and neck locations, and putting those all in a pandas data frame. And so that makes it easy. Well, one thing to mention too is I'm also taking the current state. And so that makes it easy to after the fact, like if you want to get all of the data points for one throwing motion, you can just query all rows that match the throwing state, and you'll get that throwing motion. And there's a little bit here, I have all data and history. And the reason I did that is because I wanted the history to track a single throw. And then as soon as you complete that throw, that information gets put into the all data frame. And the history will just move on to be for the next throw. And that way you can be sure that you're getting data only for this one throw if you're doing the analysis. But then if you're looking at it after the fact, you want all of the data that happened over the whole iteration, just to kind of check the decisions and stuff. So, and I'll show you guys the CSV after we do a demo. So when we update this one, like I mentioned, it checks, well, first it checks if the data is none or if the depth of the wrist is 0, and it just kind of skips that frame. Otherwise, it goes through and grabs the data and computes the distance traveled and also the instantaneous velocity. And this is all, like I said, in the depth direction. and it puts that all into a data frame row. Let's see if there's anything else here. So yeah, I was just for the eye and the neck, I'm keeping only the Y and Z. I wasn't using the X value for anything. So wasn't super interesting. And then let's see. So I have this get data function, which lets you get the data only for a specific state, which is exactly what I described for the throwing motion. And then a save function, which saves that CSV file. And that's just for debugging. So trying to see. Oh, and then the screen handler is the last piece. I said it was simple. It's the simplest thing in this whole file. Basically, it's just reading this dartboard, and then based on the list of darts that it currently has, it draws circles on the dartboard, and then returns that image to be shown on the streamer. So that one's really simple. A nice break from looking at the other classes. So I think that's everything. I think I can jump over to a demo. If there's any questions, let me know, Como, and I can answer those. But
nope, no questions yet.
All right, let's give this a try. So if you try this yourself on a Jetson device, I was running into an issue where after the first run, the RealSense camera would fail to read any frames. And so I found that by unplugging it and plugging it back in, I could get around that. But it's very frustrating. So I'm looking into how we can resolve that now. So that's one unfortunate thing I ran into. But if you unplug it and plug it back in each time, you can get it working. And I didn't have this problem on the regular Docker container on x86 Linux. So, all right. And I should have shown the. I didn't. Okay, we'll do this. There's one other or two other functions I didn't show that I think people would find interesting. But anyway, one thing is that the score just always returns 10. So you'll see that I just get that score, whatever, every time. But anyway, get into the throwing motion. So now it's telling me to throw. I throw the dart, and you see it's processing the batch frames. And then, I'm like off to the side here. So I'm printing some debug data, but we get more attempts. So let's see if I can do any better than that. Okay. I was never very good at darts either, so so look at that. And there's a lot of numbers you can tweak to kind of get this to be easier or harder. I think the first iteration I did had me get a bullseye almost every time, and I was like, that's no fun. So okay, let's try this again. Come on. Oh, I'm not very good at my own game here, or I made it too hard. But anyway, we got 2 more tries.
At least you were honest.
Yeah. Oh, yeah. So I haven't hit the board yet. This is the worst. I was trying it right before. I was doing better than this. I'm not sure. Wow. Wow. I think I need to. Okay. Maybe if I stand back farther, maybe I'm too close. Oh, there we go. Yeah, that helped a little bit. So, but luckily I got 10 points no matter what, no matter how bad I missed the board. So, yeah, so that's the app. And so the FPS I was seeing is about 13, but it's hard to gauge for this one because it's switching between inline and batch. So sometimes it's getting 30 FPS and sometimes it's getting like 8. So it kind of balances out.
How are you calculating the motion of the dart?
That is exactly what I didn't show. So I left the most interesting part for last. So I have this determined dart position, and it's not, I wouldn't say it's too scientific, and it's kind of sloppy right now. I was just trying to make it interesting. But basically what I'm looking at is I grab all the data from the throwing motion, and I find the max velocity out of that. And so I'm using that to determine if you go I kind of picked middle velocity that I saw on all my tests, and that's 8 meters per second. Sometimes it's higher, sometimes it's lower. Let's take a look. So yeah, so that's this value. So it was 4, so it was lower. Then here it was 12, so it was higher. And so, I'm having that play a factor into this, and you can adjust. So I'm multiplying this by 5, like 8 minus your max velocity. So however far off you are from 8, either sends you low if it's slow or high if it's fast. I'm multiplying that by 5. You could probably make that a much smaller amount. But even this last attempt that I had was at the right level. So it's doable still to get the bullseye. On the other hand, I'm grabbing the start X, Y, and the end X, Y, and then finding the diff between those. And so it's just kind of a simple, like shooting a straight line between the beginning and the end. Obviously, if you wave your arm all around and like end in the same spot, it's going to give you like a straight shot, which, isn't really how it would probably work in real life. But you could definitely add some more sophistication to that and understanding like the overall path rather than just taking the start and end. That was the simple implementation that I did. And then I was taking kind of the errors in the difference between the beginning and the end and just multiplying that by a factor to make it more difficult. So I just chose 10 arbitrarily. And so what that's doing is that wherever you start is kind of 0, 0, that's a bullseye. If you were to end directly on that with the right speed, you would end up with a bullseye every time if you could figure that out. If you're a little bit fast or a little slow, you'll be up or down. And then if you just kind of like throw it off in like a wrong direction like that, it's going to measure those differences and take that into account in where it puts the dart. So, and then this last one, I'm just making sure it stays within the bounds of the image. I wanted to be able to, it cleared the dartboard, but you could see even when I was like, I totally missed the board, it would still kind of put it at 0 and you'd still see it. I thought that was kind of a nice thing. So you could still see all your misses. There's a lot of fun stuff you could do with trying to make this more sophisticated. And I think I was just working through it as fast as I could to get something that'd be fun and not too easy. And then here's the famous get dart score that just returns 10 every time. I didn't have time to get to that piece, unfortunately, but yeah, any other questions?
Yeah, what is the inference time for the model, and did you enable Jetson clocks?
I did not enable Jetson clocks, and I don't know if this is Steve asking this because he's always pushing me to give that a try. That would increase or it would lower the inference time. I think the inference time for this, let me jump over to the model catalog real quick. That's not here, model catalog. So let me just jump over to the human pose ones, not pose estimation. I wonder why these, this is the same. So this is the Onyx model, and this is the TensorRT model generated from the Onyx model. I'm not sure why. I'm going to have to look into this. I never noticed that they were different, but this is the one I'm using. So I guess I'm seeing about 42 milliseconds. I didn't print that out on the app, but I could add that too as a debugging thing to better understand. Let's see. Oh yeah, so here we go. So this is what our benchmarking came back with. Like I said, I don't know why it's different between the two models. It should be identical. This one is based off of that other human pose model, so they should have the same performance at the output. But Jetson clocks would probably give me a faster inference time on this. So that's something that I can try as well.
Sweet. And then how did you calculate the release frame?
Sorry?
How did you calculate the release frame? Or is it just fixed at 15 frames?
Yeah, so I started by, so that's the hard part with the batch processing, is because you can't really know whether you stopped the throw until you do that processing. So to keep it simple, what I did was I just chose a set amount of time, and a half second seemed to kind of capture the right amount of data. There's the other factor of how quickly you can actually detect the throwing motion started. Oh, I said I was going to go through the CSV, so that'll help this too. But yeah, I just hard coded 15 frames, like a half second for that throwing motion. And it was kind of experimental. I was capturing a second at first, and you had to like really hold your follow through for a long time. So, so yeah.
So we have 2 more questions. First is are you using image XY data and then Z for depth data? And like, I think he's just confused about the axes. How does the depth axis work?
Oh yeah, so it's a little bit confusing. So the XY is just within the frame of the RealSense camera, and it's being mapped to this image. And then the depth is in meters, and that's based on like the depth sensor output and the depth data you get back from that frame. So it's not like the X, Y, and Z aren't in the same like coordinate system really. It's like X, Y in the image, and then the depth in like its own world kind of. But I was just treating it like X, Y, and Z. It was just a convention.
Okay, and then do you think the OAK-D would be able to do things similar to the RealSense that you showed in this presentation?
I think that you would. I haven't used the OAK-D myself, but this human pose model, it can also run on Myriad. So, and actually, we can take a quick look at what kind of performance it gets on Myriad. We jump back to to this one, which actually works across a whole group of things. So let's just say we're using a Pi 4 with OpenVINO. This is still going to be really slow, actually. I wonder. Yeah, it might be a limitation of the CPU on there just because of that post-processing piece. I'd be interested to find out what the impact of that is. So depending on, yeah, I mean, we would have to, I don't remember, does the OAK-D have a Myriad chip built into it, or maybe I'm not remembering the OAK. Maybe if the OAK-D is just depth like the RealSense, then I think you could plug it into an Xavier NX as well and get the same sort of performance that I'm seeing with this. I don't know if the OAK-D can get up to like 90 FPS and stuff like that. That's a good question though.
So yeah, the OAK-D, Steve just responded, and AB did as well. He said that, yeah, OAK-D does use the Myriad.
Okay. Yeah, so I'd be interested to see, we'd have to benchmark it, but the NCS2, if it's comparable to the NCS2, it looks like the speed might not cut it for an app like this. I mean, you could still make it work. It would just be a little bit laggy, and you'd have to maybe find some tricks to backtrack on your throwing data. It's actually one thing I'll point out. So this looks like a wall of data, but this is all waiting state. So this ready state is when it's trying to see if you're throwing, right? And then let's see, this last column I think is the velocity. So here we can see I've started the throwing motion. But the thing is, like, it's already, let's see how much. I think this one is much easier if the headers stay with you. Yeah, so the wrist Z, so the depth here. So we can see that from the previous one, I've already moved quite a bit. And then if we look at the whole throwing motion, I really only move a little bit. My wrist only moves a little bit more forward. So that's telling me that, and actually it should start here, that I'm actually missing a good portion of the throw still. So even that 30 millisecond delay, or it's probably like 60 milliseconds or something because of the post-processing, is causing me to make the decision that the throwing motion has started late and I'm missing some data. So one way that I think, like, one kind of hack to get around that is to actually take like the throwing ones and maybe one or two of the ready, like the ones before it, and actually capture from that point on. And you might be able to do the same thing with like that might help enough that you could use the Myriad or your laptop or something and still get reasonable performance, because you'd still capture this velocity, and this ends up being the max, but the starting point is what's more interesting, and you can see that, like in this case, kind of like moved and it came, well, yeah. So the starting point would have been significantly different if I started capturing in this like a little bit earlier. And so things like that, like it's kind of experimental. You have to mess around a little bit, but you might be able to make up for the limitations on the inference time and still make a compelling app. And it might be that if it's something that's not darts, it's not as fast of a motion, you might not care as much about that pure speed.
And I think AB had something he wanted to say. AB, are you there? Hello?
See him there.
Can you hear me okay?
Yep.
Yeah.
Yeah, a nice app, Eric. Very good use of RealSense fan for the holiday season coming up. So yeah, regarding I wanted to talk about that OAK-D. I think OAK-D uses a different human pose model. So I think they have. But I think there's also a limitation there with the OAK-D. So one thing is does not have the I think the IR based as well. So it is totally based on Studio BGM. So the accuracy to do, and it uses that disparity map to do the depth sensing. So it is not that accurate. It requires a lot of steadiness. So as well. So it is not that as accurate as like Kinect and RealSense. They're still working on that. The other thing there is, I think the batch size also, which supported by that model, what they have is I think only one as well. So yeah, I would not compare this similar application running on OAK-D at this stage using the model which they have in the Intel's model zoo. So either you train your own model, but there's a lot of limitations. So this model is very heavy, as you already said. So it is very heavy. So the post processing takes the bunch of. That's why I'm not very much excited with V1. It's very, very difficult to work with. It's not very fast as well. Yeah. Yeah, but really good app actually. I would definitely. I don't have an NX, but I would try it on laptop. Let's see how it works. Yeah.
Thanks,
Yeah, it
AB.
works well enough. And then if you're messing around with it on your laptop, you can always try and see if you can like hack, 2 frames to be in the throwing state before and grab those. You'll probably get more interesting throwing data if you hit the same issues that I did where it was just missing most of the throw. So yeah,
so
give that a try.
Could we use the CUDA course on the laptop?
We don't support the CUDA cores on laptop at this time, only on Jetson devices, unfortunately.
So only that DN, so we need to use the DNN flag, right?
Yep.
Okay, cool. Thank you. Thank you, Komal.
Yeah, thanks, AB.
Yeah, thanks.
Okay, we have lots more questions, Eric, if that's okay.
Should I stop sharing or?
Yeah.
Let me see. I can see well, actually, I'll just stop sharing. I can see the questions here though.
Okay. The first question is, what was the max difference in wrist depth?
So there's that's a good question. So if I'm looking at my data, it looks like it's like 0.6 meters change, or actually that's not even. Let me see. So sorry, I'm not sharing anymore. But anyway, it's just a wall of numbers anyway. So wrist depth here. Oh, it's not even. It was like 0.3 or 0.4 meters. But I was, like I mentioned, sometimes I was seeing the case where it would lose the wrist and jump to the back of my office and say it was like 4 meters. And so I had to kind of filter those cases out.
Okay, and I think his follow-up question was, is it close to the length of your arm? So
I think that Like it would, yeah. I mean, that's a good point. Yeah, it would be close. I mean, I have to measure my arm to see. I don't usually think in meters, so I'd be interested. Like, I never actually looked at these depth numbers in terms of actually like seeing if they were how well calibrated it was and how well they were working. I was just kind of like taking the output as is. So something like that. Like you would expect it to your motion to kind of be close to the length of your arm, and that'd be an interesting way to actually verify how much of the throw you captured in the data. So that's actually a very useful debugging technique that I'll probably try after this. see how it lines up. But yeah.
Awesome.
Thanks.
And then he also asked, outside of this project, have you tried linking multiple models together? I'm working on an autonomous RC car.
So as far as like linking multiple models. So one thing that we have some examples out there of is that you can load and do inference with multiple models. And so I think we have an app where you detect a face, cut it out, and then from there you can determine like age, like we have an age estimation model and stuff like that. And so in that way, I'm not sure if that's what you mean by linking multiple models, but we have that, and that will work on like DNN engine. I haven't tried it on Jetson, on the CUDA stuff, TensorRT and stuff like that. There might be limitations. Supposedly, you can run multiple models. You can load multiple models onto the NCS2. We don't currently support that. We supported it on the NCS1 because their API was a little bit friendlier for handling that, but I haven't looked into it since we moved to the full like Intel API on the NCS2. But supposedly it's supported there too, so it's something we'll probably look into at some point. So yeah. And it sounds like a cool project with the RC car. That sounds super cool.
Yeah, share with us what you've built when you have a chance. It'd be cool to have you on someday, maybe, Alex. This one's from Dale. He's asking, are you doing pose estimation in RGB space with no depth?
Yeah, the pose estimation is just on the RGB frame, no depth there. So what I'm doing is I'm doing the pose estimation, getting the key points, and then using the key point to get a depth reading from the depth aspect of the RealSense frame.
And we have a question here. Any time frame on when you might support NCS2? We already support the NCS2.
Yeah, so if that's referring to the multiple models, I don't know if we have a time frame on that. I think it's kind of in our backlog, and if it's something that you really want, like feel free to chime in. Yeah, I mean here you are, but even on Discord, like it's good to know what our users want. Sometimes we're making decisions a little bit in a vacuum, or it's something that we want to build an app. So yeah, like be vocal on Discord. Tell us you want something, and that's how some of these things get prioritized. And we make sure that we get them in. So awesome, thanks.
Yeah, and if you're not on Discord, I'm entering in the Discord link in the chat, so you can use that to just join our Discord channel and ask any questions. And then we have one that says, would it be possible to see or track an actual physical dart in motion and calculate the motion from those images?
I believe the answer is yes. But I don't think we have anything that you'd be able to kind of do that out of the box right now. I imagine you'd have to train a model to kind of to be able to detect where the dart is, and then also you need something like an FPS, like a RealSense camera that can get you a high frame rate, like 90 FPS probably, maybe even faster. I don't know I've never tried to capture something moving that fast, but I imagine you need something with a really high frame rate to make sure you can accurately detect it. You don't have just a blur going across. And so I imagine you could, like all these pieces could come together with the RealSense and probably Xavier NX if you train that model and stuff. And then the depth piece would be a whole extra aspect. I imagine you could do it all, but like the depth of the dart you might have to have a really sophisticated algorithm that checks like a whole bunch of points and determines, because if you think about like that depth map, if you're off by just a little bit on a dart, you're going to be hitting the back of the room instead of the dart, or like, I just think you'd have to be like very careful with that, but it seems like it could be done. I don't know.
I think that's it on questions for today. Alex did mention that he said he needed an additional model to track the flight of the object and do some motion estimation with that. Any comments on that, Eric?
Yeah, I think you could do that if you kind of had an understanding of how you expected the dart to move and stuff like that. And this doesn't have to be all like, I mean, not all of it would be computer vision, and not all of it would be machine learning either. I mean, it might be just some stuff you can use with like more classical signal processing techniques if you're able to track the dart, if you're able to get dart location from using computer vision techniques. So a lot of different ways you could do something like that. I remember seeing a demo somewhere where someone had an overhead camera on a pool table, and they were tracking each of the balls individually. And so when someone would go and hit one of the balls, it would track their paths all around the table, and it was a pretty sweet demo. This sounds kind of like similar to that. Obviously, the cue ball is going to move a lot slower than a dart probably, but kind of a similar idea of tracking the paths and stuff.
Nice. So I think at this point I'm going to wrap up the Q&A session. We are about 8 minutes over time, but before you all go, I just want to let you know that we are hosting a webinar on December 1st, and the focus of this webinar is computer vision is changing the world. And to find out how, you can join us at Hacky Hour, of course, but if you want to see specific applications and use cases from our community of developers, this is your chance to come see it and maybe have some inspiration for your model training challenge. So definitely sign up for this. I'm going to share the link in the chat. And we do this every Thursday, so at 2 p.m., join us every Thursday, except for Thanksgiving, because we will take that off. But we're doing this next week, and we'll be joined by David Tischler from Balena, who will show you how you can deploy computer vision on multiple Jetson devices using Balena Etcher. So please join us for that. And thank you again, Eric, for joining us and sharing this really cool application. And thanks to all of you for joining and watching us and asking questions. We're really happy to have you as part of our community, and we'll see you next week. Thanks, everyone.
Thanks.
Take care.